Where is it? There it is. Okay. The ideal gas law. Again, the big goal, I think, is to be able to predict nature, kind of pretend that we can control it. But pressure is a really interesting thing. Aaron, why do airplanes, or how can airplanes fly? You ever thought about that? Does anybody know? They're definitely heavier than air, right? Okay. Do you recognize this shape, anybody?
Looks like an upside down.
Yeah. On an airplane, though. On an airplane, have you seen this shape? You pretty much have to, I don't know how you have to be at the right angle, maybe, facing the plane. You're facing right down, looking right down the wing. The wing is going to have this shape, this kind of oddball shape. And it might be kind of changing, and they've spent a lot of time and engineering to get this just right. But the shape is going to be something like this the whole way down on the wing. Does that make sense? It's kind of curved on top, but it's very flat on the bottom. Okay, are you with me so far? All right. This airplane, he's going to take off from San Antonio, go land in Austin. Is the air going with the plane, or is the plane going through the air to get to Austin? He's going through the air, right? So this plane is not taking San Antonio air with him. Does everybody agree? So it's landing up in Austin, it hits Austin. So that means, now imagine this wing going through the air, right? So if you're air on top, you have to go over the top of the wing. Kind of like this little division right here, I guess, right? If you're above the dotted line, you're going to have to go over the wing. If you're air on the bottom, you have to go under the wing. But you stay, so you both have to reach the end of the wing at the same time, right? Because you're staying. So this air is going like this. The bottom air is just going straight. Make sense? Which air is going faster? The top, because the top has to go a farther distance. Make sense? Okay. Now, before I shouldn't have drawn that yet, but where's atmospheric pressure in all this? The wing's in the atmosphere, so where's atmospheric pressure? It's everywhere. It's everywhere, right? Top and bottom. Fine. All right? So if you want this wing to go up, you don't want it to go down. That's gravity. You want it to go up. Does the pressure above the wing here have to be smaller or bigger than the pressure below it? It has to be smaller. Atmospheric pressure is everywhere. So you're going to have atmospheric pressure on the bottom. You have to have something less than atmospheric pressure on top. Okay, it has to be. Otherwise, it's not going to, there's going to be no lift, is the word. So what's the next logical thing I want to say? The next logical thing I want to say is, okay, so that means air moving fast has to be at a lower pressure than air moving slow. Air moving fast has to be at a lower pressure than air moving slow. And that's what gives a plane lift. Do you believe me? It's easy to say, but do you believe me? It's kind of hard to believe, don't you think? Okay, I'm going to show you. Rubber stopper with a hole in it. I'm going to blow as hard as I can through that stopper, right? Onto this little card, right? Blow as hard as I can. Okay, so you have atmospheric pressure everywhere. Air on top of the card is going to be going out this way, right? Air on the bottom of the card is just there. It's atmospheric pressure. But the point is the air on the top of the card is moving fast. It should be at a, what pressure in comparison to the pressure below? It should be at a lower pressure, smaller pressure. It's counterintuitive. I'm blowing on this bloody thing as hard as I can. I should be blowing the card to hit Alyssa in the face, right? But if I blow as hard as I can and that card hits the ground, every plane in the sky right now is going to crash. Law of the physics just changed. Okay? So now do you believe me? Or do I have to prove it to you? I have to prove it to Monica. Okay. A good thing I'm not a smoker, and this is why you can't smoke, because you couldn't do this. See? If it didn't work, man, planes would be crashing. Okay. Now another interesting thing I think about pressure is what this dude found. If you're the manufacturer of New York's cheddar kettle potato chips, you don't want that to happen. No one's going to buy that bag. They're just going to take pictures of it with it, right? The problem is for that potato chip manufacturers, where I think this gets interesting, is the kid's kind of sweaty looking, right? It's got to be hot. It could be in the middle of Texas. The AC's gone down in this ice house, this gas station, right? And this potato chip bag's about ready to blow up. Now, all these potato chip manufacturers are stuck between a rock and a hard place. It'd be nice to have a vacuum inside that kettle chip bag, right? Because then you don't have to worry about this happening. They're probably going to last longer, right? Don't get stale as quick. But who's going to buy your chips? You suck out all the gas in a bag, it's going to look like there's nothing in it, right? Everybody's about quantity when it comes to food. So no one's going to buy it. So you got to put some gas in there. And you don't want to put too much, because when things heat up, gases expand. I mean, the dang thing looks like it's ready to break, right? So you got to put in the right amount. I think the company just put in too much in that one. It's a mistake, right? But either that, or that's just how they manufacture them. Maybe all the bags are on the aisle blowing up. Okay, ideal gas law equation. Kelly, what is the ideal gas law equation? What is that equation? Remember? Something equals something. Anybody? PV equals nRT. There it is. Okay. Caroline, how many variables are in that equation? Yeah, but one of those, you're right, there's 5 I guess. R, though, isn't really a variable. R always equals the same thing. No matter what the problem is, no matter what the gas, no matter what is going on, R is always the same thing. R was, you remember you're using this in the, yeah, you've got this memorized by now if you did the homework. Liter atmosphere over mole Kelvin, right? And there's different R's you can pick, but this is the easiest one. So really there's only how many variables? Everybody, there's only 4. Any homework question in the exam is going to give you how many? They can't give you 4. There won't be anything to do. They're going to give you 3. And then you solve for the 4th. That's how every single problem is going to be. Okay. What are the units for each is the only place where you can screw up, I think, Paul. Pick a variable. Tell me what the unit's got to be. P is atmospheres. Keep going. Alyssa. T's got to be the kelvins. And Priscilla, how do you get things into Kelvin again? If it's in Celsius? Add 273. Talia, another one? V is volume, which has to be in what units? No. Here's a hint in here. Has to be in. Anybody see it? Liters. Last one is little n, everybody? Moles. Good. Okay. So the ideal gas law equation, but with molecular weight. Another equation. Something equals something. Jared, what's that something equals something for the equation ideal gas law but with molecular weight in it? I don't know if you caught it. You had to kind of recognize it when you're writing down the definitions of all this stuff for today. Anyone remember seeing it? Big M is a hint. Big M is in it. PM equals, no one saw it? Dirt. Okay. Let's play the same game, April. Give me a variable or give me a letter and tell me what its units are. T is temperature. That had better be in what units? Kelvin. Monica Soto Ruiz. P is ATM. There's our pressure. Eric. Not molarity. Molarity was concentration. That was moles over liters. Yeah, right. Big M was that symbol for molarity, but they want it to be molecular weight. Remember, when you add stuff up over here, Eric, you always got what units or what unit? Grams over moles, right? You add stuff up on the periodic table, you get molar mass, grams over moles. Okay, there's a couple left. Jasmine. D and R. Which one do you want to go for? The R is same R? Yeah, the same R. So we already know what the R is. Okay. Monica Lopez. What is that little d? It's density. Very good. That's density. Okay. Density was always what over what, Aaron? You remember this? Density was always mass over volume. So it has, our density, Kelly, it's got to have mass over volume units. So looking at what the units are for that R, looking at the units, you got Kelvin. What is missing that you're going to have to put in, and it's going to be the density units. And Aaron gave you a hint. Mass units over volume units. And it has to be stuff we haven't used yet, right? Because look at, can you see what it's going to be? Now the mole part, right, because liter atmosphere per mole Kelvin is our R. But the mole's already here. So, yeah, our density's got to be what over what? Ooh, she saw it. To get this to work, the density has to be in units of grams over liters. Because you have to have the same units on both sides. And you could play the canceling unit game and see that, you know, the units cancel out, they work out. The only way to get the units to work out is if density is grams per liters. Okay. So important, because otherwise you're not going to be sure how to use the equations, right? They got to be in the right units. Here's our first problem. Caroline, here's our first problem. According to your calculations, a reaction should yield 5.67 grams of oxygen. What do you expect the volume to be at 23 degrees Celsius, 0.95 atmospheres? Let's try to make your life really confusing here. I've got this one to worry about. I've got this one to worry about. Now I've got PM equals dirt. All right? We could number them. So you don't have a 50-50 shot anymore. You have 1 out of 3. Which equation? She says the first one. I hear the third one. Okay. What's that? I heard the third one because there's grams in it. Okay. I think what's going to help you, maybe not. My brain doesn't always do things like the least complicated way, but here it might be. When I read this stuff, I really don't read it. I'm just looking for what they're at, because I know the game. I played the game so much. I know the variables, because I gave you all the equations. If all I got to do is read the question, see what variable they're after, and then I go look for the equation. What variable are they after in this question? Volume. So the first thing I'll probably write is v equals question mark, and then I'll go look for the equation. So you could make this one work, but it's going to be a job, because v isn't even there. V is there. It's right here, but that's going to be a job to get it. So you pick an equation with volume in it. So when I'm doing this, not even reading the question, it's going to be either 1 or 2. And you kind of skim the question a little bit more. You can rule out number 2 because look, I need a lot of variables. Exactly. So it's going to rule it down to number 1. Okay, that's kind of how I mess with this stuff. I don't know if it helps or not. Okay, but that means that we got to know what all this stuff is. We have to know what P is. We have to know what N is. We have to know what R is. We have to know what T is. Okay, there's the first question. Let's leave that one. Paul, how do you answer Summer? Would you have to convert the grams to moles? Yes, and that's going to be which variable? Yeah, but once we get to the moles, that's going to be which one of these variables? That's going to be little n. Exactly. 5.67 grams times. We need the molar mass, Priscilla, of oxygen. 16, but times 2, because there's O2, so we'd have, right, O2. 32. Okay, so 5.67 divided by 32, about 0.18, 0.177 or so, depending on how many units you want to use. Okay. Alyssa, we have to know the rest. What's another one? She said do the temperature. 23 plus 273. Thank you very much. 296 Kelvin. Okay. Summer, we need to know another thing here. Yeah, and stop there because that's the right units. Good. Oh, the R, Talia, that's got to be... here. All right. 0.0821. Substitute everything in. We'll have the 0.985, our V, our 0.177, our 0.0821, and our 296. Okay, and I kind of left out all the units because we kind of straightened that all out already. Our units, they all look good. Okay, so if you're going to do that on your calculator, April, what would you do? Yeah, good. I'd multiply all this stuff first, then what? Then divide it by the P, the 0.985. Good deal. That's exactly how I would do it too. The 0.177 times the 0.0821 times the 296. Divide that by the 0.985. About 4.4 or so. And you're going to get it docked points, Monica Soto Ruiz. If you put the wrong units on, it's got to be what? Liters. Good. Okay with it? So read the question, see what the variable is, and then choose the equation. Seems to be easier, but may not always work, but at least it's a good starting point. Eric, butane is an easily liquefied gas. If you're a smoker, you use butane lighters all the time. They call them BIC, but calculate the density of butane gas at 0.897 atmospheres and 23 degrees Celsius. Give the answer in grams per liter. Probably which equation? Third one. Yeah, it's got little d in it. So when we do figure everything out here, Jasmine, what will our units in D come out? When we use this equation, what will the units in D come out in? They'll come out in what? G over L. And that's what they want, right? They want, give the answer in G over L, grams over liters. So we don't have to be messing with anything in the end. But it's just, I want to point that out because a lot of times they like density in grams per milliliter. So once you get your answer, you got to convert to milliliters. But not here. D, that means you need to know P, M, R, T. Monica Lopez, we got to know those. What are they? 0.897. Now let's keep going. You're on a roll here. What's the next one?
R is 0.08.
Yeah, that 0.0821 thing. Let me write. Okay, and the T is, yeah, 296 again. Okay, the only thing we're missing is the M. Let's give someone else a shot here. Aaron, how are you going to get big M? It's got to be grams over moles. How are you going to get it? It's the what mass? Molar mass. So we need the molar mass, Kelly, of C4H10. So it would be 4 times what? 4 times 12 plus 10 times, Kelly, 1 plus 10. Just 58, right? 4 times 12 plus 10 times 1. Put everything in. You're going to have 0.897. 58. Our D, our 0.0821, and our T. Did you get about 2.1 or so? Hopefully. Right. If you do the math right, you should get around 2.1. Try it. Right, 2.14 or so. Did you get it, Paul? Yeah. Priscilla? All right. Take the 0.897 times the 58, divide it by 0.0821, divide it by 296. It should work. And everybody, the units have to be grams over liters. Right? Good? All right. So if you get it, go ahead and try the last one here. Then we'll call it a day. See if you can knock out EX3. Let's make sure. Do you see a stumbling block for this? They're after molecular weight. There's a bunch of questions, right? Let's start with what equation do you want to use? Yeah, I think everyone pretty much agrees with that, right? Because they're after molecular weight. That means P, M, R, T. The problem, oh, what am I doing? They were after the M, right? This should be a D. The M is what we were trying to find. Does everybody agree? M is what we're trying to find. And we should know P, D, R, and T. The problem is which one? Density. Okay. This is a two-part question then. You got to find density first. So first find D. Then we'll go over here. How do you get D? Oh, there's a start. Hear what Alyssa said? Get this guy into liters. What else do you have to do? Then what? The 1.28's on the top? Exactly. Because you know that D is some number grams over liters. So just find the number of grams, divide it by the number of liters, and you'll have little d in grams per liter. But Alyssa's right. You got to convert this guy to liters first. Once he's converted to liters, you'll have the 1.28 grams up on top. So he's the 250 mils, but make sure he's in liters, though. You got to convert them. And then you'll have your D. Then you go and you find your molar mass. Oh, I didn't even see that, Monica. Pressure's in the wrong units. Pressure's got to get in the 760. That's a good point, right? You got to convert those pressure units into atmospheres. And I give you all the relationships. 760, yep. Exactly, equals 1 ATM. That is a good, I didn't even notice that. Pressure's in the wrong units. So convert that into ATMs. So those are the numbers I got for P, D, R, and T. Plug them in, solve for your M. Anybody get an answer? 160? That makes sense. I have to divide the grams by the liters. So convert 250 milliliters into liters. All right. 1,000 mils in a liter. So that's going to be 0.25 liters. So that number goes in the bottom. So the density is going to be the 1.28 divided by 0.25. And you get 5.12 grams per liter. Yeah, because density is grams over liters. So you divide the 1.28 by the 0.25 liters. Caroline, did you get an answer? You get 160? All right, so it sounds like several folks are getting somewhere around 160. Make sure you have the right units on or you're going to lose some points. That's a final answer.